Welcome to the SAFECode e-learning course, Threat Modeling 101. The goal of this course is to provide you with information about threat modeling. By the end of this course, you'll understand the idea of threat modeling, and you'll be able to execute a basic threat model yourself. By understanding threats, risk, and risk rankings, you'll have the capabilities to interpret the results of an executed threat model. We will also provide you with additional resources to extend and improve your threat modeling knowledge. The primary audience for the course is software developers, architects, and test engineers. However, anyone involved in the software development process will benefit from it, as having an understanding of the threats that an application might face and how to structure those threats is helpful from the very beginning of the development lifecycle. This course starts with a basic introduction to threat modeling. It shows the purpose and benefits of utilizing threat modeling. After you've gained an understanding about the basic threat modeling concept, an important tool used within the threat modeling process will be presented: diagrams. We'll discuss how diagrams can be used to establish a common understanding of your evaluation target and to identify threats. Before we finish with a short threat modeling example, the general process of threat modeling will be explained in greater detail. Now let's start with the fundamental basics of threat modeling. Threat modeling is a natural activity. We do it all the time and don't pay attention to it. Whenever we make a decision that's based on perceived chances of something good or bad happening, we are applying threat modeling. It may be a long, protracted process like deciding where to invest money, or it may be a split-second decision of when to merge into the next lane of traffic. Basically, we're considering the pros and cons of a given scenario, possibly deciding how we can fix things that go wrong in that scenario, and then deciding on how to proceed. Fortunately, we don't have to make split-second decisions when designing and implementing computational systems, but we also don't have the advantage of a long, slow, drawn-out process. We need to be able to identify what might go wrong before it does, and fix it before it becomes a problem. We play what if with the possible scenarios to decide which one makes the best use of available resources inside the constraints we operate under. Having budgeted for and completed this process, we ship. And then we have to do it again when the system changes. In this course, we'll give some suggestions and basic rules on how to execute a threat model. Whatever decision on methodology you make, keep in mind that you will have to understand your system well enough to know where it might break, and that you will repeat this exercise every time the design is changed, new features or functions are added, a new version is developed, a new interface is added. For these reasons, above all, you should aim to have a clear process that can be easily repeated, generates results that carry over into the next iteration, and provides as much coverage in width and depth as possible. Risk may be simplistically defined as the cost of a problem weighted by its likelihood to occur. When we rank possible threats against each other to decide which one to fix first, the risk calculation is a candidate to be used as a ranking factor. Fix what brings most risk to the product. Of course, quantifying the likelihood depends on knowledge about the threats and is not an exact science. The likelihood changes from threat to threat, and even for the same threat among different systems and scenarios. Impact, on the other hand, will almost always be a function of the business case applied to the system being examined. The centrality in this discussion is that the risk will basically be the foundation around which we'll decide which problem to tackle first. Absent other constraints, those problems with the most risk must be addressed first. Of course, the big picture must consider security as one of a broader set of business risks. Elevating security risks above more serious business risks could be a mistake, which increases ambiguity further. In the context of threat modeling, a security risk can influence a higher-order business risk adversely. For example, a security breach might affect brand recognition, which consequentially may lead to business risks. In that case, the compounded risk elevates the security risk even more. After focusing on threat modeling and risk estimation for everyday tasks, let's switch to secure software development. By utilizing threat modeling within the secure software development process, one is able to identify, classify, and prioritize risks that threaten the product. By using a consistent, repeatable method and a clearly measurable risk ranking driven by threat modeling, more secure software can be developed. Systems may begin to address security at any point in their life cycles. Ideally, for maximum return on investment, it would always be done at the design stage, but that's not always the case, nor even always feasible. Threat modeling can occur at any time in the software development lifecycle, and the results used for security improvements. With that, note that the quality of a threat model is a direct function of how much information about the system is known as we start the process. Eureka moments, when the team figures out how something really works, should be minimized by having prior agreement on the workings of the system being modeled. The team needs a consistent and precise view of the system when starting the exercise. This is a rather important precondition. Input can be provided by different departments. Developers know how the software is built. Sales staff know a customer's stated plan for using various feature areas, and customer support knows how customers actually use the software. Getting input from all of those stakeholders helps to create a broad view about the system. The actual process of threat modeling is simple. Identify the components and the way they interact by creating a model. Identify the threats these components and their interactions are subject to. Mitigate the threats as needed. Validate the mitigations, and then begin again at the next iteration. Also remember that systems are constantly evolving entities. Performance, compatibility, and feature changes result in frequently updated code and architecture. The process of threat modeling, therefore, reflects this reality by being cyclic in nature. Once we identify a threat and proceed to mitigate it, we may introduce changes that by themselves warrant further modeling, which might uncover new threats, etc. The same happens at the validation step, and meanwhile, new features are coming in. It's important to accept this cycle as part of the secure development reality and make sure that results from the previous threat model are included in the next iteration, if only to offer a view of past hurdles and to guarantee that they do not reappear, which is important for long-term improvement. It's also important to know when the current threat modeling cycle is complete. Besides the technical side of security, there is a real-world component that cannot be ignored. The business case of the product is part of the threat model in the sense of determining the amount of security that the product should support. For example, a promotional video game that has no business or personal data associated with it should not command the same level of security resources as a product that will contain the absolute crown jewels of a customer and is expected to withstand continued attack by a nation-state level adversary. Technologies in use are another business factor that relates to security. Some programming languages, for example, are more susceptible to specific weaknesses than others. The same goes for infrastructure and platforms, and some web servers may offer a larger exposure than others. Also, think about assumptions regarding the environment the product will be placed in. Is it a very hostile, open environment, like an internet-facing web application? Or are strong measures like an isolated environment, physical access control, and similar characteristics expected? Ensure that your chosen assumptions are based on validated facts and are well documented. Factors like the maturity of your organization and the amount of resources that can be dedicated to security are also important in figuring out the priority of mitigations. From a purely pragmatic view, security resources should be allocated as part of a balancing act that guards the organization's current and future ability to function, compete, and protect itself and its customers. All these factors are part of the threat modeling decision process. Let's now turn to a very important tool used within the threat modeling process: diagrams. They are important because they're very valuable in creating a common knowledge base. First, model a system overview. This overview should visualize high-level processes as well as data stores, and it should include the data flow between components and external actors. When creating such a diagram, you must make sure that it really reflects the system. Confer with the appropriate knowledgeable people so that you create a complete representative diagram. Sometimes it's necessary to create separate diagrams for different functional areas of the system. Also, some parts of the system might be of special interest and therefore warrant more detailed diagrams. This simplistic diagram shows a very high-level view of a generic system. A user interacts with a server, which interacts with a database. No details about the data flows and modes of communication are offered yet, and no helpful details about the system's inner working are apparent. But even at this high level, some possible threats become apparent. If we want to defend the confidentiality of communications, for example, we want all communication between user and server to be encrypted. We want the host holding the database, and we want the database itself to be hardened. By breaking down the big elements into smaller pieces, we can see that the user side is actually a two-flavored interface, with a browser acting as a GUI and an API CLI. Both use similarly named data flows, reflecting the fact that they both share the same characteristics. On the server side, we break it into two distinct units, which might denote separate environments, one for the web and business logic components, another for the database. It can be seen that some of the elements are already decomposed as much as possible. For example, API and CLI show their dependency on open source libraries like readline and libcurl. On the other side, larger elements that are outside the development responsibility of the product team, such as the database server, are expressed as higher-level components. At this resolution, the data flow details are pointed out. Data flow 1, for example, will be specified as being HTTPS, with certificates on the server side to guarantee authentication of the server at least. Then, based on the business case and system requirements, the possible risk of lack of client authentication would be raised and would demand either mitigation or negation. Data flow 2, on the other hand, would require more architecture information. Is it a network link, or does it happen as inter-process communication inside one single host? By repeatedly drilling down on elements and pointing out architectural requirements, the complete picture of the system is constructed with enough information for educated and sufficient analysis of risks and possible mitigations. Once the diagram starts taking form and detail as a result of adding more detailed breakdowns of subsystems, it's time to annotate it with details about the processes and data flows themselves. We're interested in anything that plays a part in security. For example, for an individual process, it's important to know the language it is developed in, as some will be susceptible to some kinds of risks, like buffer overflows, where others will not. The identities under which processes run will help us mitigate abuses of the least privilege design principle, and so on. Sensitivity of the data and data transformations are complex issues on their own, but more so when taken into consideration jointly. Data acquired from distinct sources categorized as low sensitivity may have its sensitivity promoted by joining other pieces of data. For example, a date of birth might be considered low sensitivity personal identifiable information, but if it is maintained under the same level of access as a national identification number, an attacker may be able to join both pieces of data and construct a higher sensitivity piece of data. For this reason, it's vital to keep tabs on the way data is stored and transformed inside the system. It's clearly a daunting task to maintain the annotations. For that reason, it is important to clearly and uniquely label all elements so that they can be easily referenced by supporting documentation. At the end of the process, you will have a diagram of the system and an accompanying piece of prose that explains the contents, behaviors, and relationships among parts of the system. This will be the blueprint for performing a complete and effective threat model exercise. Here are some obvious but useful tips. A threat model is, at heart, a design-level exercise, and the process reaches a diminishing return point when detail goes beyond the single process and into code as written. While there is value going to code to find out the details necessary to annotate an element, it is not necessary to drive analysis into the actual code or implementation in most instances. Putting all elements into a single diagram may not make for easy reading, and important details may be missed. It's more efficient to have clearly labeled diagrams that focus on specific logical chunks of the system, all mapped out on a larger block diagram showing how they interact. This is especially true when different teams develop distinct parts of the system. When using a whiteboard to create a diagram of the system, it may make sense to use transparent overlays to offer levels of detail or annotations. For example, in one layer, the data flows show which ones are encrypted and which are not, and on another they simply appear as connecting lines, letting focus rest on the processing elements themselves. While whiteboard drawing is a useful tool when discussing the system, for the final results of the threat model, it's advisable to develop an electronic format diagram that'll be easily edited in the next iteration, making it easy to start and to keep documentation and annotations in sync with the system design. One way to ensure that all elements of the product are covered, especially on larger systems, is to think through the different use cases. Experience shows we hardly ever forget about the core functionalities, but we have to work to ensure that we also include less common elements. For example, backup and maintenance functionalities are often overlooked in such exercises. There are no standard symbols for composing a threat modeling diagram, but over time some conventions have developed, like the ones depicted on this slide. There's nothing stopping your team from choosing whatever symbols make sense for them, or extending as necessary. As one example, double concentric circles are often used to exemplify complex processes that will be decomposed in a separate diagram. Until every element is identified and described, continue annotating the diagram. Some annotations are absolutely necessary for a good threat model, even if they don't belong to any element in particular. Analyze and mark where authentication and authorization is needed and where it is implemented. Sometimes there are also underlying circumstances influencing parts of the system. For example, a specific communication channel provided by a third party uses weak encryption and cannot be changed. This type of information does not belong to any specific element, but it's very useful to use it and augment the diagram with it. Of extreme importance is the identification of sources and sinks of untrusted input. We classify as untrusted any input that can be tampered with without the knowledge of the system, or input originating from unauthenticated sources. These will, more than likely, require special care such as additional sanitization and validation, elevation to a trusted status by means of verification and authentication, etc. Formally, a trust boundary is an interfacing of two entities that have different privilege or sensitivity levels. Any data crossing that boundary needs to be scrutinized so that its content can be guaranteed to have not been modified in transit by an attacker, that is, tampered with, that the declared originator is actually the real originator of that data. That is, the originator has not been spoofed, and that the originator cannot claim not to have originated the data, meaning the data cannot be repudiated by its originator. Trust boundaries may help isolate parts of the system and lead to better understanding of the ways privileges are required and used around specific elements and data flows. For example, if a process running in one host talks to a database on another host, chances are that there is a process of credential exchange between them, creating a trust boundary, since each actor has a different set of privileges and level of trust. In this sense, trust boundaries are useful to help us map the places where important security mechanisms, like authorization and authentication, might go wrong. The complete set of interface points where something might go wrong is called the attack surface of the system, and a large part of it, though not all, is defined by its trust boundaries. Trust boundaries work not just in small scale, for example between processes, but also on a larger scale, such as deploying applications in a cloud environment. There is a trust boundary between the application parts running in a cloud environment and the parts operated internally. Additionally, there might be trust boundaries within the cloud, for example to the applications of other cloud customers, or the platform operated by the cloud provider's staff. Once your diagram is complete and all stakeholders agree that it represents the totality of the scope of the system to be modeled, it's time to validate it. There are many factors to consider and ways to validate the diagram, but here are some of the main rules of thumb. First, make sure that all data has a place where it comes from and a place it goes to, and that these are well defined and annotated. Actors usually create data, and data stores keep it at rest. Second, look for disconnected elements. If an element does not produce or consume data, it is probably misplaced or misrepresented in the diagram and should be examined again. There should also be no instances of data moving from an actor or a source directly into a data store. There needs to be at least one intervening process, such as a database client, a process that inserts data into the database, etc. Data going from source to storage indicates the lack of a middle step that either validates or transforms the data. When we have a complete validated diagram representing our system, we can start the actual threat modeling process. As we have previously stated, the quality of the threat model will be a direct function of the clarity of details and complete coverage of the system being modeled. Once we have achieved that level of understanding of the system, we're able to start identifying threats against it, which is by no means a trivial task. The main obstacle to achieving this is lack of knowledge and/or experience from the participants in the exercise. Sometimes knowing a threat is not enough to enable seeing how it applies to a given system, or how it applies to the system at distinct levels. For this reason, many teams make use of a subject matter expert, an SME, in their first iterations, someone who will help point out where the system may be under threat, understand the associated risk, and help the team acquire a basic understanding of the method. In the absence of an SME, the team may turn to a number of formal methodologies for threat identification, like Microsoft's Stride, or using a predefined library of threats. We'll talk more about Stride in a little while. The methodology that works for each specific team and product is the one preferred. Experience and the circumstances of each iteration will help determine the best approach. We give pointers on some of these methodologies in the references at the end of the course. Besides identifying new threats, it's important to turn to previous iterations in order to examine any findings that have not been addressed and to validate the effectiveness of the solutions for those that have been. The role of the SME in a threat model is one of a mediator or guide, imparting more refined experience to identify obscure threats that may not be immediately apparent or may not be part of the threat library in use, as well as sharing mitigations that actually work. It should be one of bringing solutions together with findings and not just findings. The SME is a partner and a stakeholder. At the same time, it's important that the SME focus not only on threat identification and mitigation, but also on the transfer of knowledge. There are few available and capable SMEs compared to the number of product teams in need of guidance. Depending on an SME is clearly a model that does not scale. This last point cannot be understated. The presence of the SME must be aimed at educating the team, not solely to serve as the security expert who will be responsible for all output of the threat model. Threat modeling is a team sport, and while each individual is important, no single individual should own the responsibility of threat identification, and the system will probably outlast the present configuration of the team. The value of threat modeling lies in the ability to identify threats and knowing where the biggest levers for increasing security are. To achieve this, we first must evaluate which weakness exists that allows the identified threat to occur. We also have to think about who could be a threat actor. It's not always a stereotype attacker. It could also be some user authorized to have physical or logical access, who's creating a threat just by negligent behavior. Sometimes specific circumstances must exist for certain threats to occur, so we need to identify the when. To identify the worst threats, the potential resulting impact must be evaluated. There are various ways to rate the impact and likelihood of a threat, but keep in mind that using a defined rating scheme allows you to compare different threats from different systems as well, so that you can decide which threat must be mitigated first and should receive the most immediate attention. Stride, compiled by Microsoft, is a taxonomy of threats that compromise well-established properties required for secure systems. Its name is an acronym for 6 categories of threats. Spoofing. This is an attack vector whereby a malicious actor masquerades as a different and typically more trusted identity. In a properly secured system, all actors are authenticated, or the system is explicitly designed for anonymous access. Tampering. This is the inappropriate alteration of data or state by inappropriate parties, compromising the integrity of the system. Repudiation. The non-repudiation security property ensures that sufficient logging and other controls are in place to ensure that no actor can deny taking an action for which they were, in fact, responsible. Information disclosure. This refers to a breach of confidentiality, the disclosure of data to individuals who were not intended to have access to it. Denial of service. These attacks threaten the availability of resources and functionality to legitimate users who depend on them. Elevation of privilege. This occurs when vulnerabilities permit actors to complete actions for which they are not authorized. Altogether, Stride provides an easily remembered framework to help drive a threat modeling process. The taxonomy draws upon security principles such as those described in the first section of Salzer and Schrader's influential paper, The Protection of Information in Computer Systems. This content is easily comprehended and remains valuable today. Although we've already used the term threat library, we had not yet provided a formal definition and examples. A threat library is an organized list that would contain minimally distinct kinds of threats that any system might be subjected to. For example, from OWASP Top 10, one could use A1 injection as a possible threat to interfaces receiving arguments to SQL, OS commands, LDAP, XML, etc. Or a more generic design error like CWEs, CWE 306, missing authentication for critical function. Both can be identified as threats to be mitigated, and specific elements in the system may be identified that are more prone to them than others. The choice of threats is crucial. If your domain is more susceptible to a given threat, make sure it appears in the library at the expense of less prevalent ones. For example, if you're using a threat library to model a web application, it's sensible to say that threats like SQL injection and cross-site scripting will take prevalence over, for example, CWE 366, race condition within a thread. While these others should not be forgotten, they're not as prevalent in the web app domain as they are in kernel-level development, for example. The entry must contain the way the threat manifests itself and the kinds of elements affected, processes written in C, data stores, unencrypted data flows, etc., and must express the technical impact of the threat so that informed decisions may be made about the risk created by the threat and possible mitigations. Pointers to OWASP Top 10 and CWE Top 25 are available in the References part of the course. The objective is to visit each element, data flow and/or interaction at least once during the process. At each visit, the chosen threat determination methodology must be applied to the item in all facets and layers so that existing threats can be identified. This may be as simple as asking, "Am I vulnerable?" questions, as proposed by the OWASP Top 10 in their entries for each weakness. Once a threat is determined to exist, the next step is to establish whether it's already been mitigated, either by some provision of the design, implementation, and business choice, or if it has been accepted as a risk in the system. In either case, the finding needs to be documented with the appropriate detail in order to make the next iteration and the next model easier and more detailed. Threats mitigated in a past version may become current again if factors in development alter the mechanisms that serve as mitigations previously. It's important to point out that in the process of mitigating newly found threats, care must be taken not to introduce new vulnerabilities and weaknesses. Mitigations may also introduce changes to the design, which will by themselves force a reevaluation of items already examined but newly changed. Some basic rules of thumb apply to data flows. Whenever there is a connection between two elements, authentication may be necessary. 1. The client, or both client and server, endpoints of the data flow may need to be assured that they are indeed speaking to the other party they expect to, and not to an impersonator that may be in the middle of the conversation. We point out that they may need it simply because, in some scenarios, it'll be acceptable to the system, based on expected behavior, to not know or care about the identity of its clients. For example, at least not at this level. But almost always there will be the issue of authorization. Is the actor utilizing the data flow authorized to do so? Are all the operations carried out in that data flow protected by an authorization check? This is especially relevant to those data flows that straddle trust boundaries, but all data flows should receive this examination. We've already mentioned how the issue of injections is a top weakness identified in most threat libraries. Injection is a prime example of data passing over data flows that may not have been scrutinized for unhealthy input to the system. The data may carry partial SQL syntax that will break SQL queries once the data is merged with the query format string. For that reason, the same argument made for authorization must be made for data moving over the data flow. Has it been validated when entering a process to guarantee that it contains only what the process expects? In the same way, are we sanitizing stored data to contain only what other parts of the system expect to receive and process? There are no actual specific rules on when to stop the exercise, but at this stage, it's easy to see that the main issue is coverage. If we leave even one element outside our analysis process, we may be offering a substantial avenue of access into the final system in the form of an exploitable weakness. For that reason, it's important that each element be visited at least once, and its security needs must be considered. If constraints dictate that not every single element may be visited, then priority should be given to those that require authentication and authorization, or that straddle a trust boundary, as those tend to be the most sensitive ones. Of course, this is an extreme decision and might leave the system widely exposed to unmitigated weaknesses. There's also the view that if only a certain number of well-known and defined threats interests the modelers, then the elements should be checked solely for those. This is a very restrictive view and will possibly not be applicable for the majority of circumstances. At other times, constraints beyond the control of the team may be present and force the decision to terminate the exercise. If that happens, or seems bound to, it's important to consider the previous three conditions and make sure that at least one of them can be reached before the end of the exercise. During threat identification and mitigation, it's important to keep the boundaries of your responsibility and influence in mind. If you're planning a desktop application, for example, it may be part of your business model to consider that another specialized application will be responsible for keeping the platform clean of malware and not invest in malware-related resources. Or you may consider that a rogue sysadmin might have legitimate access to the system. The privileged user is the attacker in that situation, and decide that this risk is the responsibility of the customer. Also, keep in mind that there is some low-hanging fruit that may be tempting to push to the customer or user, such as responsibility for logging events. But even in that case, it's your responsibility to provide enough logs, clearly stated with only the necessary information, correct timestamps, and possibly non-repudiation verifiers, that'll make the customer's logging responsibilities simply about receiving, storing, and triaging logs, and not maintaining a forensically sound timeline of events from your system. Guidelines that clearly state to the customer your basic requirements for secure installation, such as physical security mechanisms, controlled access, etc., will help mitigate some of these risks, but consider whether they need to be part of your threat modeling exercise. To recap, we have diagrammed the system, annotated its characteristics on each component, element, and data flow, and we have analyzed it for possible threats. We're done, right? Not quite. Now we need to take that output and arrange it in a way that makes sense for the process of triage. What should be fixed, and what urgency should the fixes have? In order to do so, we should be able to rank the findings, put them in some kind of order so that we know what finding is worse than any given other. In other words, as stated in the introduction in the course, we need to evaluate the likelihood, impact, and resulting risk of each identified threat. Best practice is to establish a defined rating scheme to ensure that results of different projects and releases are comparable. There are, again, many distinct methodologies for how to do that. One popular example is the Common Vulnerability Scoring System from FIRST, the Forum of Incident Response and Security Teams. We'll expand more on this example, but for now, we'll just say that it produces a numeric score that translates to the risk of a given finding, which can be used as a badness index to order findings from must fix now to good to fix when possible. The Common Vulnerability Scoring System, version 3, or CVSS version 3, has been designed by the CVSS Special Interest Group at FIRST to, quote, help organizations prioritize and coordinate a joint response to security vulnerabilities, unquote. It aims at ranking vulnerabilities by quantifying values such as the access vector used to exploit the vulnerability, how complex it might be, what level of authentication it requires to be exploited, and what the final impact on confidentiality, availability, and integrity of the system might be. It's common to see practitioners of threat modeling simplify the calculations of a CVSS score by using only the basic metrics group described, leaving the temporal and environmental factors for incident response teams. There is another initiative in progress, CWSS, at MITRE. It is still in the definition stage, and it aims at providing a better method for prioritizing weaknesses relative to each other and with the other issues of the application. It will probably be a valid alternative to CVSS once it's well defined. CVSS only recently moved into its current version 3 in June 2015. Once the exercise is done, take another look at the results. The diagram, after the application of mitigating changes on design and definition, still needs to match the final product. Make sure you didn't lose functionality or add more moving parts than necessary while mitigating design flaws. You should have a ranked list of results showing the threats identified, their mitigations if any exist, and the proposed mitigations if not. It's very important that this documentation contain enough information about the identified threats and the scenarios where they occur so that test cases can be properly built to validate the mitigations. If you cannot create a scenario that will help a tester understand and try to exploit the vulnerability, it has to be reassessed. Inherited risk from third-party components should also be assessed. While this might appear to be endless work, it's important to take their own threat models, or if none exists, at least their hardening procedures into consideration as something your product will also inherit and carry forward. The system has been mapped and annotated. The threats have been identified and ranked. Now the question is, what to do? Of course, the initial response is to go over the list of findings ranked by severity and criticality and solve those first. But many times, that solution is inappropriate for a series of reasons. Some additional questions to add in the ranking calculus would be, should I solve a more severe problem that occurs with a very low likelihood? For example, one that depends on a hard race condition or on certain esoteric configurations being present, or a less severe one that can be exploited every single time an attacker attempts it. To decide which to choose, the amount of impact on the system and the customer may be the deciding factor. Also, depending on the product's stage in its life cycle, it may be more costly to fix a design flaw than to throw smaller but less certain mitigations in front of the problem, which will act as bumps on the road. It's a balancing act to decide on a path that suits the security and business needs of the product. Time and effort spent mitigating possible threats is time taken away from other business goals, like developing new features or improving on existing ones. This opportunity cost will vary depending on the size of the team and even on the size of the organization. A large organization may be more robust and accept greater risk than a startup establishing its brand. Be sure to factor in these issues when considering how to proceed with mitigation. Threat modeling in an agile environment is a subject worth a training module by itself, if such were possible. There are many flavors and styles of agile out there, and it would be difficult to embrace them all in one formula that fits everyone. Instead, we recommend embedding the practice of threat modeling into the recurring sprint process as one more activity. Perform it in the scope necessary to cover new features added as the system evolves, and from time to time, but at a well-defined cadence, approach the whole system looking for threats. Make sure that this activity is protected from overflow by reserving a number of points for its execution, and by bringing it up to the storyboard every time as needed. Adding a refresh or update to the threat model as a condition for done will help formalize this part of the process. The potential amount of information created or sublimated by a threat model is considerable. Not only will threats be found and be in need of cataloging and following up, but potential discovered information about the system architecture and mechanisms will need to be maintained too. All this information needs to be produced and maintained in a way that your team will be able to quickly follow and utilize. Once the mitigations are executed and verified, those threats that did not get addressed need to be well documented for future mitigation. All the information needs to be kept up to date so that the next round of modeling can benefit from it. Let's demonstrate the whole process with a quick example. Your company is designing a new consumer application that will track health and fitness information, conceptualized to help users make positive lifestyle choices. The application collects and stores basic personal information plus their medical histories. As a result, the information is considered sensitive, and a breach would have a significant negative impact on your company's brand image. The application will offer the user both mobile and web interfaces to interact with the application, using standard HTTP protocols for communication. Luckily, you were involved early enough to have the opportunity to assist the product team during the design phase of the application. You have assembled stakeholders from the development, testing, and product management teams to create a threat model of the application. Together with the stakeholders, you review the proposed architecture and begin to diagram, making note of external actors, high-level processes, high-level data stores, and the data flows connecting them, keeping everything at a very high level. This helps to bring the entire application into the scope of the discussion without dwelling on any specific details. Even at this very high level, possible threats begin to emerge. At this level, you simply diagram the web and mobile users, as well as the web and data layers of the application and the simple flows between them. Ensure that the product team agrees on this 30,000-foot view before moving on to the next phase. In this phase, some threats can already be identified. You will need to protect the communication in transit between the users and the system. Protect the system against impersonation of a sysadmin by an unprivileged user, and protect the database against unauthorized access. Continue the exercise by repeatedly drilling down into the various elements, detailing the various architectural requirements, being careful to appropriately detail the security-relevant components until you have enough information for educated analysis of risks and possible mitigations. A process would be an appropriate level to stop drilling, since the next step would be source code. Black boxes detailing multiple processes can also be a good stopping level, as long as it's understood that all processes in the same box act at the same privilege level. Of special interest are those places where trust changes. These are commonly called trust boundaries. They mark a division in the flow where the level of trust changes. A user goes from anonymous to authenticated. A valid user becomes a privileged user, etc. These interfaces and the associated authorization operations are common and recurring sources of security problems at the design level. Interaction of the system with the platform can be a vulnerable point. For example, calling an executable with data provided by the external environment via a system call is another example of trust changes that need to be policed. For sensitive data, the definition is left open, but three basic types of data are important: user or customer data, system data, and platform configuration data. All three are of interest to an attacker in different ways and for different reasons, and all three merit protection at the system architecture level. Bringing those identified threats down to a more detailed level of the model, we can see the communication path between the browser and the web server component. You have annotated the browser with the input and output it'll be producing and consuming in the form of HTML5, JavaScript, JSON, and XML to encapsulate data, apart from the usual ways of HTTP to transfer data via headers and URLs. You've also taken note of the HTTP transport for critical security functions, as well as data manipulation. You have confirmed with the group that HTTPS is only used for security-critical functions, as HTTP is preferred for performance reasons for regular application access. You also note that HTTPS connections are terminated at the load balancers, and all communication from those devices to the web servers is sent in clear text. You have inserted trust boundaries to represent segments of the corporate firewall and have annotated the application server with its underlying technologies as well. Working through a previously created threat library that already contains those most prevalent to web technologies, you identify several threats that apply to the proposed design. Man-in-the-middle attacks, because HTTPS connections are terminated at the load balancers. Sensitive information such as credentials is traversing network segments without encryption. Because of this, other servers on the web server's network segment could potentially perform a man-in-the-middle attack via ARP cache poisoning against the server and steal application users' credentials. Session hijacking, because traffic after login is sent via HTTP, there is a potential to leak session credentials over HTTP. Cross-site scripting, because the application allows individuals to register and enter personal information. There's a risk of cross-site scripting if this data is allowed to be stored without sanitization or later returned to the client without proper encoding. Now that all threats have been identified, each threat is discussed for the purpose of ranking and prioritization. Discussing the threat of cross-site scripting, you suggest that the team may want to adopt as a standard OWASP's ESAPI library for sanitization and encoding wherever untrusted data is introduced or later used in a response, or that a layer of sanitization be inserted between the data layer and the web layer in a centralized way. You mark this as a critical risk in accordance with your threat library, and you note the proposed mitigation so that this can later be tested for proper implementation. You move on to the session information leakage threat. The team recognizes the risk of session credential exposure and the need to protect session cookies. In fact, in their secure coding guidelines, this issue is specifically called out and regularly addressed by ensuring that the secure flag is properly set. Satisfied with this proposed mitigation, you record it so it can be later confirmed, and you mark the risk as high in accordance with your threat library. You move on to the final threat, clear text transport of sensitive data. The discussion of this threat stirs a good deal of debate. Some team members refuse to see this as a problem. Acting as a subject matter expert, you discuss with the team the real-world risk of man-in-the-middle attacks and back this up with an example from a recent breach that made headlines. The security of the network is further taken into consideration, and representatives from the network team are brought in to assist and clarify details. Ultimately, it's decided that this risk cannot be mitigated, as the termination of HTTPS at the load balancers is a hard requirement of the networking group, not likely to be changed anytime soon. Besides, the few other servers on that segment are hardened and have a limited connectivity to the outside world. The team concludes that they cannot mitigate this threat at this time. You marked a threat as high in accordance with the threat library, and the reasoning of the team not to mitigate it is clearly noted. Per policy, this threat is later elevated to the business stakeholder, who takes responsibility for its acceptance. After the threats are identified and their scenarios, mitigations, and risks are ranked, you help the team create a comprehensive test plan for these issues. The cross-site scripting and the cleared text transport of sensitive data are entered into the bug repository and marked as security bugs with the appropriate ranking and their CVSS scores. The drawings and documentation are maintained as living documents in the team's repository, but protected from general access as sensitive information. Your first threat model is done. In this course, we've learned how threat modeling helps to strengthen the security of a product. Through applying well-established methodologies, we're able to find threats that potentially negatively affect the product. Threat modeling supports project teams in identifying, prioritizing, and finally mitigating relevant security risks. Diagrams with a different level of detail, threat libraries, and methodologies for risk evaluation help to create a transparent and well-structured way of executing a threat model. Please ensure that your threat models are updated as your products change over time. Here are some links and resources that you might want to explore to develop your understanding of how to conduct and improve your threat modeling further. Thank you for taking this course.